Thank you. Thank you very much. It's my fault. Nice to meet you. I would like to indeed present the results we obtained on the fatigue behavior of the interface between WAAM and a substrate made of structural steel. My name is Davide Leonetti, and I am from Eindhoven University of Technology in the Netherlands. I would like also to acknowledge my co-author, H.Heydarinouri, from the Swiss Federal Laboratory for Material Science and Technology, EMPA. Wire and dark additive manufacturing is, as you know, an emerging technology, especially in the construction sector, because it allows very high deposit rate and therefore relatively quick fabrication of additive manufactured components. It falls within the category of direct energy deposition methods, so it's sometimes also referred to as a dead arc. It's essentially based on MIG welding, so it's sort of automated welding that deposit basically the welding wire over successive layers, and therefore it's relatively simple as compared to other additive manufacturing processes. Basically, to exploit the advantages of WAAM, recently many works have been presented featuring hybrid manufacturing. That's basically a manufacturing method that combines, let's say, components which are produced following traditional routes like profiles, pipes, tubes, together with the additive manufactured part to indeed fabricate maybe some complex attachment or joint in such a way that it's possible to combine the advantages of both and mitigate the limitation of WAAMs, especially in terms of cost and fabrication requirements. For example, in some studies, these are tests that we conducted in our laboratories, exploit WAAM within a hybrid manufacturing framework to, for example, prevent buckling of this built-up steel section, steel column, in such a way to exploit the full capacity of the structural element without the occurrence of buckling. Other advantages or disadvantages, depending actually a bit on the point of view and the failure mode, is that WAAM might alter residual stress fields. Certainly alters residual stress fields, and in some cases this could lead actually to have some beneficial outcome, like indeed in the case of buckling, where by adding additive manufactured material at flange tips, we obtain a tensile residual stress field that instead of a compressive one, which is in favor of let's say, does not allow buckling to occur, pushes away buckling load essentially. Within the hybrid manufacturing, the WAAM has been used also to, in some studies, to rethink structural connections. For example, like in this case, this hinge beam to column connection has been idealized through making use of WAAM attachments, which can be seen here the way they've been fabricated on the right-hand side, the pictures. Or, for example, for stiffening structural elements in a different way than done usually, for example, close to the point of load introduction, by optimizing the shape of the reinforcement in order to help the load to spread to the structural element. Well, within this framework, we were wondering about the fatigue strength of actually the interface between the wire and arc, the additively manufactured part, and a substrate of structural steel in this case. Because, yeah, there are many studies that look at the strength of the additive manufactured material per se, the effect of notch, and so on, but not so many that look at the interface. So we basically idealize this specimen is an attachment made by additive manufacturing, made by WAAM. Both are basically structural steel grades. So this is the base material here is S235, very mild, low carbon structural steel, and the corresponding welding wire has been used to produce the additively manufactured attachment. In this case, for the test that I'm going to show you today, no preheat of the substrate plate has been executed. So it's directly, the additive manufactured attachment is directly printed on top of it, which could indeed resemble a sort of worst case scenario. The printing pattern is essentially straight. So successive layers have been deposited on top of each other in a linear pattern, and settings of the machine in terms of heat input and cooling time are those, let's say, standard for this kind of production, and was suggested by MX3D, which is a renamed company exploiting WAAM. So you can see here the specimen on the left-hand side. And actually, if you look closely to what will be later on the critical notch, given the way we are going to load this attachment, you can see that there is some, let's say, penetration of the additively manufactured material into the base plate, especially towards the end, probably because of the heat that was a little bit higher than in the central part. And we also see the formation of a notch. So there is not only, let's say, the notch due to the intersection of the additively manufactured deposited material with the substrate, but also a notch due to the waviness along the edge of the additively manufactured part. As you can see, there is a little bit of chamfering. So the component is not straight. Does not have a uniform cross section along the deposition direction. Well, that is essentially because we wanted to ensure failure at that location at the interface. We weren't sure whether that would occur in case in case of a uniform cross section, essentially. So this is a picture of the test setup. We use an electromechanical test bench with a capacity of 50 kilonewton that is loading the attachment in a cantilever fashion at the frequency of 20 Hz and the load ratio of 0.1. We use an LVDT to measure specimen compliance. At least that was our initial plan. But due to the fact that the actuator is equipped with a digital position sensor and the rest of the road train is very stiff, we actually found more convenient to use the displacement of the jack because it's very accurate and pretty much noiseless. In correspondence of the point of load application, the edge of the attachment has been flattened in such a way to avoid secondary loading to be introduced, and the load is introduced by a rolling pin type of configuration. The attachment, actually the substrate plate, is connected to a relatively stiff frame for the loading that we are applying. So we can neglect the deflection of the frame, and it's attached by preloaded bolts. This is a picture of the fracture surface for the attachment. As you can see, we can clearly distinguish a fatigue region and the final fracture region. One of the main features that we can observe, well, we essentially observe three things. The first thing is that during a fatigue crack growth, essentially the crack path, okay, except for the initial transition, but I'm gonna talk about that in a moment. The crack path follows really the intersection of the top first surface of the substrate and the attachment. It is a bit, I thought of the same effect of side grooving in a CT specimen, right? It keeps the crack planar somehow. But in the final fracture region, well, it's not very obvious here, but the crack path seems to follow the fusion line of the deposited material. If we look closely to the point of crack initiation, we see that the crack did not initiate at the intersection between the additive manufacturer and the substrate, but at the first notch. Well, it's actually a second notch, depending on how you look at it. But let's say at the intersection, at the notch generated between the first and the second deposition layer, the crack grows a little bit in a sort of mixed mode until it reaches the other plane, in which it keeps growing until the final fracture occurs. First of all, one of the evaluation that we wanted to do is whether we can use, for this case, the structural details which have been, which are indicated, recommended in the Eurocode. And I show you here as a constructional detail what we thought is the most suitable one, a load-carrying transverse attachment loaded in this direction, where you would expect indeed it's a load-carrying attachment. In this case, the weld length is smaller than 8. The attachment length here is smaller than 80 millimeters. So in our case, it's certainly smaller than that. So we use the detail category 71, and we don't consider redistribution of stresses due to that should be considered in some cases when the attachment is connected to a base plate which is not stiff enough. So given the dimension of the attachment, the base plate, and the rest of the frame, the fact that we use bolts, we think that there is no load redistribution. So we didn't verify that, but yeah, thicknesses are very large for the rest of the components. So it will be very strange to have load redistribution. So here you see the fatigue test results, which let's say align here almost perfectly. And the detail category 71, which is a good lower bound for this test. Well, it's meant to be a lower bound, right? So it's a good lower bound for this test data. We also observe that the slope of I don't show here a fitting line through the test, but the tests are pretty much parallel to detail category 71, meaning that the slope of the possible SN curve will be very close to 3, indicating the dominating mechanism of crack propagation instead of crack initiation. Well, together with this analysis, we also build up a very simple fracture mechanics model in which we have a semicircular crack nucleating at the top of the cross section and correspondence of what we found experimentally, and developing until an extended surface crack is generated, and this will grow up to a failure condition, which is not specified in this case in terms of fracture toughness, but in terms of either validity of linear elastic fracture mechanics or till the end of the validity of the equation to calculate the stress intensity factor. This is based on the assumption that since we are doing a full life estimation, well, in this case, fracture toughness would have certainly an effect on the size of the critical crack, but not so much on the number of cycles to fail, predicted number of cycles to failure, because by the time we have a true to thickness crack, we have consumed most of the life. So yeah, it's a generic assumption which can be made in this kind of prediction. We assume a semicircular crack having this shape, which is in accordance with some guidelines for assessment of welded joints through fracture mechanics. As a crack growth rate curve, we're going to employ a two-stage crack growth curve, as those suggested in the British standard. Essentially, we consider, even though our loading ratio is 0.1, we consider the presence of tensile residual stresses by considering a loading ratio larger than 0.5. Therefore, we consider this highlighted parameter for stage 1 and stage 2 crack growth. Well, the only thing to mention here is that we perform an analysis using both the mean curve and the lower, actually upper bound curve of this fatigue crack growth rate, relation, considering a mean plus 2 standard deviation values, keeping in mind that this will be overly conservative because these parameters have been obtained, these are reported in the British Standard 7910, and it's are obtained by pooling different data sets for many structural steels, weld material, heat affected zone. So this is potentially a very large scatter which you will not encounter if you perform fatigue crack growth rate test on one specific material. So this is the prediction of the fracture mechanics model. We have here a mean prediction and the lower bound, and we can also see that more or less the lower bound is located indeed at the lower bound of the data set and in between the data and FAT 71. Ultimately, we want to check the agreement between the let's say the crack growth curve, the AN curve predicted by the fracture mechanics model, so not only in terms of number of cycles to failure, but also in terms of AN curve, indeed between the fracture mechanics model and what we measure during our test. By schematizing our specimen like a cantilever beam with the torsional spring at the encastre. During the test, we measure not only the load, but also the deflection of the specimen. And this, as you can imagine, is an increasing compliance while the crack grows. Therefore, by using this quantity and the combination of these two relations, which are from the work of Scorza et al., we are able to sort of create a mapping curve between the deflection, measured deflection, and the crack size that we expect to be developed in the connection. When we compare this one with our prediction, well, of course, we see that they don't match in terms of absolute values because we were performing a lower bound kind of prediction, but the slope of the curves and therefore the crack growth rate predicted are very much similar and they are parallel to each other. So besides, let's say, absolute value and specific crack growth rate parameters, for this type of model, this level of approximation, we are confident that we can bring this to a higher level of accuracy. So going to the conclusion, I would like to mention that we indeed performed this test on this load carrying dead arc attachment on a steel substrate. There are some details perhaps to be investigated more related to the geometry of the notch at the plate intersection. The attachment was loaded under bedding loading, and generally we see that the nominal stress approach with FAT 71 approximates the results, let's say, reasonably well. And also a pretty simplistic but effective linear elastic fracture mechanics model provides a reasonable lower bound in agreement with the experimental findings. Well, for sure, the compliance base, to outline some future step we will take, for sure the compliance-based estimation of crack length can be improved, especially to detect a little bit smaller cracks than those that actually bring some visible difference into the deflection of the connection. We're going to exploit a different loading condition, especially tension and static ones. We'll investigate the effect of preheating and different manufacturing constraints like heat input and cooling time. We'll also check more in detail the macrography of the cross section to check whether actually the static failure occurs along the fusion line. We will also investigate different partners and potentially in the future scale up to hybrid connections. Thank you very much.